My talk will be called How AI Can Extract Secrets from Electronic Chips, because I didn't want you to run away. So we carefully selected the talk to attract more attention. I will try to give you some background on side channel analysis. We already got some background from Roberto's presentation. I'll talk a little bit more about that. Then present you countermeasure, because I will be showing you an example of an implementation which is protected against side channel analysis by masking, and will show that it is not sufficient. And the particular target which I selected, because it's like the hottest topic in cryptography nowadays, is post-quantum cryptography. And there is one algorithm called Crystal Kyber. Maybe your organization is right now considering a shift to post-quantum cryptography. Many organizations have started thinking about that. So we will show you how we broke fifth order masked protected implementation of Kyber, which means very high degree of protection by AI-based side channel analysis. And it was presented at Real World Crypto earlier this year in March. Then I will summarize and give future work. Side channel attacks, some of you have seen this slide before, because I talk about side channel attacks since I joined CDIS. And what you see in this picture in the corner is the attack on a commercial USIM card, which I talked about in my previous presentation. So it is possible to extract a secret key from commercial USIM cards by side channel analysis. And the point is that algorithms, whether they're implemented in software and hardware, sooner or later they will be running on physical devices, which are in your pockets, your mobile phone or computers or some other devices, but they will be running on something tangible. That can be microcontrollers, CPUs, field programmable gate arrays, application-specific integrated circuit, but they will be running on something. And that something leaks information. It's called side channel information because it's not the main one. You can measure timing, you can measure power consumption, you can measure EM with an EM probe. And the point is that if you have something sensitive, let's say secret key processed by advanced encryption standard, there is a relation between the data processed, that secret, and the power you measure during the execution. And so the power is different based on the operation as well as the data. And this is what makes side channel attack possible. It's very difficult to hide this relation in practice. So now I will introduce masking. It's a very nice, simple idea. If this is a secret, which you see in the middle of the string, let's partitioning into 2 or more randomized shares. So we will be generating a string, and then we will take this string, take a XOR of that string with a secret, exclusive or bitwise, and so we have something which is not dependent on the secret any longer, right? We can split into 2, we can split into more. The example I'll show you, we have 6 shares, so we split it 6 times. And I mean, the idea is the more you split, the less it will be correlation. So that's the point. So this is what you see in front of you. It's called first order Boolean masking, because you take one share, one randomized share, and create a combination with a secret. Now I will give you some background about Kyber algorithm. There is an ongoing process. NIST, National Institute of Standardization, is currently standardizing algorithms which are supposed to be secure if and when large-scale quantum computers become reality. We don't know if they will become reality, but we should be preparing for this. This process was going for already roughly 5 years, and there is a first algorithm suggested in July last year, Crystal Kyber. It's the algorithm you will be doing for doing key exchange. Like nowadays we use Diffie-Hellman, and Kyber is suggested to securely exchange a key. Shared key will be later used, for example, as in advanced encryption standard, but it's a key establishment protocol. So Kyber is decided by NIST. In Europe, as I know, this process is still ongoing. There are some candidates. And then there are some other candidates considered in the round 4. So at the moment, the process is in round 4. There are also some dropped candidates like Psych. But Kyber is the one which is decided by NIST. To give you a flavor of the algorithm, if you would like to have a key exchange, that you'll have 2 packages within a suite. One package will be the standard encryption and decryption and a key generation. This is PKE, public key encryption. It's a public key cryptography. And then there is another group which is doing encapsulation, decapsulation, and also key exchange. And that's basically the level I will keep you. I think it would be more useful for you to see the protocol, how you will establish the key. So we have 2 parties. It could be a server and a client, for example. I don't want to take sides, what will be these parties, but some parties. So party 1 is generating a fresh pair public secret key and sending it to the party 2, the public key they send, of course. The party 2 is doing the encapsulation, and here you see the steps of the algorithm. We don't have to go into details, but the encapsulation is running encryption and then gets this key encapsulated within encryption. So basically the message which is encrypted is something you derive your shared key from. Party 1 will decapsulate, getting that message out of the secret and getting the shared key from it. And what you see here at the end, it's actually the first 2 lines you see in the pseudocode are sufficient to get the key. However, they rerun encryption, they do re-encryption, and this is called Fujisaki-Okamoto transform, in order to assure that this algorithm is resistant to chosen ciphertext attacks. This is on the cryptographic level assured. However, what happens with side channel analysis, you can get around this chosen ciphertext attack and still do a chosen ciphertext attack, because we don't care whether the algorithm continues and whether transform pass. We only try to measure power consumption and get the secret. So you see, transform will not pass, but it's not our problem because we have measured the power consumption. So we can still do chosen ciphertext on Kyber in spite its theoretical resistance to that, because it's not about us seeing what happens, it's about us measuring power consumption. And there has been different attacks exploiting different steps, decryption and encryption and re-encryption one. I will be focusing on one of them in this attack, but both can be exploited and one can exploit at the same time. Another thing I'd like to mention, I will be presenting attack on Kyber, but it's not specific for Kyber, so I don't want you to have impression that something is wrong with Kyber, because I even heard that there were some people suggesting not to standardize Kyber in Europe because of that paper we presented at Real World Crypto. That would be very wrong, because this vulnerability I'm talking about might be applicable to other algorithms as well, because it's actually about the coding style. There are, of course, specific things for Kyber, but it may be equally applicable to all other candidates, or in fact to the candidates you are considering in your organization, because if you're one of these organizations who do not want to use standard algorithms, you'll probably tweak something in the algorithms which are standard and use it then. Still, it can be applicable to your algorithm, in fact. So that's why it's nothing specific about cyber, it's more general than that. The assumptions we make is that public and secret key pairs are kept static, because we need to do some repeated process with the same pair. We also assume that chosen ciphertext can be decapsulated. The attacker can give the decapsulating device its own the ciphertext which the attacker decides. So here is what was going to happen. We will have 2 stages. The attacks I'm going to talk about are called profiled attacks, and they are the attacks which made possible by deep learning, artificial intelligence, machine learning, call it, but this is what allows you to do that profiling, because you're creating a leakage profile of the algorithms you're attacking. These profiled attacks make possible new classes of attacks. They also make possible something which was not possible before. So what we will do, the attacker will try to get a device similar to the target device, if possible, if the attacker knows the algorithm which is run on this device. And then generate pair of secret and public key. That's the first line by running the generation algorithm. Then basically follow the steps and then run decapsulation algorithm. Notice that it's a public key cryptography, meaning the attacker can select any set of randomly generated messages, encrypt them, because you use a public key for encryption here. So the attacker can get ciphertext which encrypt known messages for the attacker. And this is important because these are your labels for training your deep learning model. If you wouldn't know the messages encrypted, you wouldn't be able to train your model because you wouldn't be able to create a label set of data. So this trick would not work with advanced encryption standard algorithm because it uses the same key. Here we know it's a public key we use for encryption, so we can do it. And it's important. Then the attacker will train the model, that's the last line, which is learning leakage profile of device. It's another device. In this case, it's a profiling device which the attacker is using. Once we have a model predicting, for example, byte values, or bit values in our case, I think we're predicting whether they're 0 and 1s. So it's a very simple binary classifier which tells you if it is a 0 or 1 processed within traces. Easy to train, you will see a very simple MLP structure we're using. So then we have two types of attacks. You may be after shared key, which is exchanged in this session, or after the long-term secret key, which is in the device and which is used for multiple sessions. If it is a shared key the attacker is after, then the attacker will eavesdrop on the communication between the parties. There is some communication keys generated, sent to the other party encapsulates, sends back the ciphertext to the party 1. The attacker measures power consumption during the processing of the device, gives this power trace to the train model at the profiling stage, and gets the message encrypted and derives the shared key. If the attacker is after secret key recovery, long-term secret key, which will be used all over, then the attacker doesn't even need to do this eavesdropping. The attacker will give the device carefully selected chosen ciphertext so that from messages recovered from the ciphertext, the attacker can deduce the message. There is a theory how to do it and how do you construct the ciphertext. So from these messages, you get the long-term secret key. And I would like to say, note, it's only meaningful to get long-term secret key if it is a static way of keeping secret and paired key. If they are not static, if they are dynamic and updated for each key exchange, you are only interested in shared key. So some details of the attack. We are attacking this specific implementation. There was only first order available implementation, so we extended it ourselves. It's compiled with highest optimization level. If the higher is your level, the worse it is for the attacker, because it's typically more difficult to attack O3. If you attack O0, it's much easier, typically, I would like to say. We are attacking the encryption step of decapsulation, and particularly message encoding operation, it's called. All API functions in Kyber are byte arrays. So it reads in byte arrays, and then it needs to extract individual bits. So there's this decoding and encoding going on. Again, it's not specific in Kyber. There is an algorithm called Saber, which wasn't selected for the standardization, maybe due to many papers we wrote on its side channel analysis, which is not fair. It's a good algorithm, but it wasn't. It has the same operation. Many other post-quantum algorithms has message encoding and decoding. And it's ARM Cortex-M4, which you see on the screen. That's our equipment. We use Chip Whisper. It costs something like $250. So it is a very low level of entry to do this attack. You don't need anything sophisticated to do it. I would like to say that that board specific is low level noise. So if you have a much higher level noise, it will be more difficult to do this attack. These boards are low level noise. So it's bad for defender, good for attacker, this type of scenario. So here's a snapshot of encryption algorithm. I only show you to show the attack point in red for people who might be interested in technical details. This encoding is converting bytes. It's unpacking and then converting these bytes I mentioned, which represent the message, into polynomial with coefficients with certain values. So if the message bit is 0, it's 0. If the message bit is 1, there will be this value written on the street, and it's done for each bit individually. That's why we can have a classifier which just reads these bits one by one from power traces. And here is an example of implementation of a non-mask message encoding in the implementation, which is kind of a standard for implementing this type of things. It's used very similarly in other algorithms. And what is special here that I would like to stress, this mask, which has nothing to do with masking, is just name selected this way. The reason it's programmed this way, they wanted to avoid if-then-else statement. Because everybody who knows something about side-channel timing attacks that Roberta was talking about, and timing attacks were for longer than power analysis. Programmers know nowadays, don't use if-then-else. It will leak otherwise in timing. So this is the reason they did it this way. They want to avoid if-then-else loop, right? And now we are in the transition to show people who code what else you should avoid. We're basically discovering new things by doing this analysis. This is also very bad. And the reason this is very bad is because this mask, which is related to the secret message bit, it takes either value all 0 or value all f, because it's 2's complement of -1 if you look carefully into this. So imagine you have a 16-bit integer, 16 zeros and 16 ones. The difference between these two vectors is 16 units. That's a lot. It really leaks. And to show things in the and by the way, this vulnerability was discovered in 2020. Now it's 3 years later. It's still used in coding. This is the effect on power consumption on these 16-bit differences. What you see in these curves, orange and blue, are distributions of power consumption when you measure. So you measure a lot of traces, you get them distribution. So on x-axis, you have an equivalent of power consumption. I don't want to go into details. And on y-axis, you have the frequency of occurrences equivalent of this, of measurements with this value. So you see the mean of yellow, the average of yellow is far away from the mean of blue. It means we can say to which distribution a measurement occurs. And you see they're really far away. I mean, it's very rare you will see this in the attack. It's a super easy attack. If the difference would be just 1 bit, that's a minimum, you know, we have to have some difference, they would be almost completely overlapping. If they overlap completely, then you cannot distinguish. And that's what you would like to use. You would like to use a coding style so to maximally overlap these distributions. If you can completely overlap it, the attacker cannot say them apart, right? This is super easy and super bad style. So in the implementation we attack, they say, okay, we will be using masking. And what they did, you see, they just copied the code I showed you twice. Right? It's an exact copy of the code I showed you twice. So each of these masks, within that, there is still difference between distribution I showed you, but because they thought they use masking, they thought they are safe. However, there is deep learning, and deep learning can not only distinguish between 0 and 1, but also do simple arithmetic operations. It's not even arithmetic, it's Boolean XOR, but it can tell you here are zeros, here are ones, and XOR them by itself. Deep learning can do simple operations. You can train it to do that. And this is what we find out. We just measure power trace, give it to the model, it finds 0 and 1s because it's easy to distinguish, and XORs them together. That's it. You don't even have to do anything, in fact. So the question we addressed in this particular paper is how far you can go, how well it can learn n-bit XOR, because 2 bits XOR with 2 arguments is easy. So we started 3, 4, 5, 6. We just were going up and up. And at some point, it couldn't learn anymore because it was confused. Imagine you have to learn a 6-input XOR. It's 2 power 6 truth table. Well, it's probably getting confused at some point. So let me, so this is a Boolean shares I didn't press. Let me start by showing you the power consumption. Kyber is a complex algorithm, and it has very long power traces. It's a lot of operation happening. So it's a snapshot of your encryption, not even complete, some part of it, maybe 1/6 of it. And then what you do, you zoom in, you measure power traces and zoom in to see something familiar. And we're expecting these 2 masks, which I showed you on the previous slide, which are identical. Each mask is processing 32 bytes of a message because messages are 256 bits. So we basically zoom in and count peaks. That's the way you process. You plot and plot and plot a lot when you do power analysis. So you zoom it, you count peaks, we find something which look like 2 shares. We zoom in further. Indeed, they were very identical. So then we tried to do the analysis. We gave it to the deep learning, and it managed to create it managed to learn the 2-bit XOR first. And when the shares are more, by doing more splitting, it's actually the traces just start looking like this. You know, you have more intervals with 32 peaks. So what you see here, 3 shares, 4 shares, 5 shares, 6 shares, we didn't have time to go, and it was getting ridiculous to go even further because masking is a very expensive operation. Even 2-order masking will reduce your performance twice. It's like 2.5 overhead you're getting on your code. So nobody will ever implement 6-order masking. We were just exploring the limits, basically. So now let me show you the simple multi-layer perceptron we're using. We like batch normalization as a very nice procedure, use it. And then you basically have one layer, input layer, batch normalization. Then you see two free dense layers, 1, 2, and 3, which are the main. We usually have a cone-like structure, which works very nice for power analysis. You have one output, which tells you the probability whether the bit is 0 or 1. Batch normalization and between usually work very nice. So that's a structure which works magic for us. It was nice. I'm giving you example with a 2-input XOR, so it's like 64, 32, 16, so it's a very simple network. Our profiling strategy, we measure 32K traces, then we cut and join them, we call them on bytes, just really virtually cut them and make the union, and train it allows us to helps generalization. And then we use message values for training. We say, this is 0, this is 1, this is 0, this is 1. It learns. It does XOR itself. So then you can ask, well, but it is a masked implementation, so how do you know where exactly is your byte or bit? Well, we try. We gave everything to the model, the long power trace. So what you see on the top is that complete power trace I showed you before. And how do we know it's there? We count number of peaks. So we give it, and what you see below, it's a plotted weights of input batch normalization layer, in particular gamma parameter of batch normalization layer. So these are weights of a model. If weights of a model are high, it means they are significant for the model. The weights which are not high, which are low, around 0, they are not significant. That means it's redundancy you can remove. So when we see these two peaks in that batch normalization of a model, you see, here where the 0 and 1s are. So these two peaks are from where the model deduces whether it's 0 and 1, and then the model XORs them later. So what we can do, we can cut the areas around these peaks, join them together, and then retrain, because if you remove redundancy from the model, this is like, I don't remember, it's like 4,000 points. So if you can just, we cut 32 point intervals, join them together, then you get a few percentages high accuracy usually if you remove redundancy. Of course, you can always say with a lot of data, but it takes time. I prefer to remove redundancy. So what you see here is the copy-paste method, which is the core. So we're cutting, pasting, and trying to go for higher number of shares, one by one. And then at some point, the models couldn't learn anymore. So what you see is here is the last model we were able to learn with 5 shares. Then we got these peaks in the batch normalization. It still was able to learn. And then we made 6 shares. It wasn't able to learn anymore. We try a lot. Many people in the group try random guess. When I mean not able to learn, I mean random guess. And then when we were looking into the peaks and say, well, they look so identical. What if we copy-paste the last piece? And rather than starting from a randomly selected state, which you typically do when you train, we give the model this artificially created. So you can look at it as a transfer learning, but not exactly, because you artificially create a model. This model never existed before. In transfer learning, the model you give existed before. So we actually cut, we copied everything you see, cut the last bit, 32, and appended it, and gave this to the model as a learning state. From the first press of the button, it learned immediately higher than 90%. Then we did some adjustments. So we extended, retrained, and we had it. And actually, I think one can go like this, I don't want to say forever, but for quite some time with this retraining. You just don't have to. But that was very interesting, because what we did, we combined human intelligence with power of deep learning. Because deep learning, well, it can do a lot of processing, but it's not that it's smart. In fact, I call it lazy and stupid. It just has a lot of processing power, right? So what we did here, we said, okay, but we know, right? We know what's going on. It doesn't, we know. So we pushed it into the corner of search space, into the right corner of search space, and then it was able to learn. So the search space was so huge, it was getting confused. But we knew, we pushed it, and then it managed to see the light in the end of the tunnel. So then we got it and managed to break it. So now I will show you in the remaining time, I have some tables of the attack. If you just give a single power trace and try to recover bits, the probabilities you see in the first line is what you're getting. And these are bits within a given byte. So you see 0 to 7, and you see for the bit 0, you have very high probability. And this is what you need. You may say, wow, that's high. 7, it's 90. You say, but 90 is good. It's not really good because you have 256 bits in a message, right? So I show you for other W and below, pay attention to this little column below, not column, table below, which is a row. That little table shows you the probability of a complete message recovery, which is the probability of bit recovery power 256. And when you take something less than 1, power 256, it goes down very quickly. So you see, even if the probability is on the last line of the table, big one, 97.99, taking power 256, you get 0.056% probability of full message recovery. You basically don't recover, right? So it needs to be very high. It needs to be 99.9996 or something. It needs to be to recover with a good probability. So what we did with that, we applied, I'm going back to one slide, rather than using just single slide, we rotated. Because what we did, we combined the expertise in our group with expertise in another group in CDIS, in fact. In fact, that happened last CDIS conference, so it's so useful that we have CDIS. I talked to a PhD student of Johan Hoster, Joel, and I told him we have this problem. Probability decreases as we go from 0 to 7, and because Joel is doing project in post-quantum crypto, for him it was like this. He said, but we should rotate. And we had no clue what it is, because this involves very high, very heavy math into the lattices, which we don't know, but he does. He does a PhD in this, right? So Joel tells us rotate messages. He explained us how to rotate. We rotate it and it works. And what we basically do, we rotate the bits which are not leaking so high into the bit position 0, which leaks very high. And then with this additional 4 rotations, we can get all the bits with a high probability and increase the success of the attack. So basically something which was not possible before, with Joel's help, became possible. So wonderful. Great expertise transfer within a project, within a center. So then basically you see these probabilities, and again with cyclic rotations we can get 87% probability of full message recovery for the fifth order masked implementation, which is very, very highly protected implementation. So the conclusion, masking doesn't work in this context, basically. So, and now there is one more point I would like to tell you. Masking is updating random masks at each execution. And this is supposed to be a good thing. But what happens in our case, it makes our measurements more independent than they would be if we would just repeat. And independence of errors allows us to really grow the probability of recovery with repeated, as we do next execution and next execution. We would never able to get such a high recovery probability if we would do a repetition attack where the same input is applied all over and it's not masked. But because masked are updated to each execution, which is supposed to be a good thing, it backfires here. And we get independence of errors in our predictions by our deep learning model. And we increase the probability. So it's actually a super amazing thing. We can do better attack than in a non-masked case with repeated measurements in a masked case. Right, so to summarize, some higher order mask implementations of Kyber can be broken. We have already tried breaking another one, because there was another one we were contacted by the person who did it when this paper occurred. We broke that one as well. It's it's all about implementation style, as I say. Cyclic rotations were very useful tricks. And future work, we definitely need stronger countermeasures for side channel analysis of software implementations. And it's not only Kyber, it's any implementation which has most likely have similar problems. And we are analyzing hardware implementations because hardware is supposed to be more difficult to attack. Things are happening in process. In parallel there, we are attacking masked FPGA implementation of Kyber presented last year at NIST Standardization Conference. We broke it actually, and writing a paper about it. Ongoing analysis of our own, we are trying to protect as well. That's what we are after. We have one implementation which we cannot break ourselves today. And there are hopes, but it's for hardware. We don't have anything which we cannot break today in software. Software is easier because things are processed like reading a book. It's instruction by instruction. So thank you very much for your attention and for everybody who supports our research.
Thank you, Elena. Questions? Wait for the microphone, otherwise we cannot get it on tape.
I mean, you said it yourself. It's like reading a book sequentially from start to end, right? Which also suggests a sort of obvious question for me. What about concurrency? Could you parallelize some of these implementations and use that to introduce
Bitwise
noise?
implementations are more difficult to attack. The second one, this one is not bit sliced, but the second one, that author which they bit sliced some of the parts. So the parts which they bit sliced are more difficult to break, but they haven't bit sliced everything because it's not so easy. So we are attacking the parts which are not bit sliced, but do go for bit slicing if you can. And not only byte, not only 16 bit sliced, up to 32, because the more is processed in parallel, the more difficult it is for us to distinguish.
Hi. Do you think it's enough with better implementations, or do we need better algorithms that can be implemented safely?
That would be nice, probably as well. The more you parallelize, the more difficult it is for the attacker, because it's all about distinguishing between the means, right? I showed you the case of distinguishing between the 0 and 1. If it is 32, for me, it means that I have to build a deep learning model which can distinguish between 2 power 32 different outputs, right? So parallelize as much as you can. Algorithms, why not? Certainly. There is somebody on the back.
All right.
Okay. Did anybody consider running some kind of multi-party computation or obfuscation scheme locally in your computer? So like you simulate the multi-party computation of the computation you would like to compute, and then you recover what the result is. And so every part of the computation is done under encryption locally.
I don't think so. I haven't heard.
All right. No more questions.